In this introduction video, we're going to discuss section 6.2, where we're finding the area between curves. And I'm breaking it two days because I'm going to start with the simple examples today, and then the next day we'll discuss more complicated examples. Okay, so what's going on is before you found, when you did integration, you're finding area because integration is area, and you found the area under a curve, and it's more specifically, you found the area between a curve and the x-axis. And if it was above the x-axis, it was positive, and if it was below the x-axis, it was negative. Now they're going to ask you questions where they want you to find the area between curves, and when they say between curves, they want a positive area. So there are a couple of tricks. So first I'm going to draw you a picture where we just are going to start with just generically what's going on. And we're going to start with the simplest case. So suppose I have some function f of x. And it's concave down. And then I have g of x, which is concave up. So this is g of x, and this is f of x. And instead of finding the area under or between those curves in the x-axis, this time I want to find the area between them. So I want to find this area right here. I want to find this, actually, hang on a second, I want to do something a little different. I want to do it like this. I want to find this area between the curves. And notice I'm drawing straight lines. I'm kind of representing rectangles. Because remember, the area we started off, we were finding rectangles. And then when we get an infinite number of rectangles, we had the exact area. So now, suppose in this time we've got, instead of the rectangles are going all the way to the x-axis, what if it's just going between the curves? How do we do that? Well, for starters, we're going to pick one cross-section. We're just going to pick this cross-section right here. This is a perfect example. For this cross-section right here, we're going to find that length. Because remember when we found area under a curve, we were finding the height of it was f of x1 and f of x2 for all the different regions. This time, instead of finding just f of x, we're going to find a length where this length, let me use a different color. This length right here, that length is equal to the upper curve. In our case, the upper curve is f of x, minus the lower curve, which in this case is g of x. So let me just write this down here. This is the upper curve, and this is the lower curve. And by always doing upper minus lower, this makes it always positive. And when they want you to find the area between curves, they are looking for a positive area. So we always want to keep this positive. All right, and you'll notice that they intersected, and that's part of it. If they don't intersect, then they have to tell you from over what region they want you to find the region between. So in this case, when they just say, I want to find the area between two curves, you have to assume that you're going to have to find at least 2 points of intersection, possibly more. So in this case, this intersects right here, and we'll call this A. It intersects here, and we'll call that xb. And so we're trying to find the area between f of x and g of x between a and b. Those are points of intersection. And the easiest way to think about this is we're really doing two problems at once. we're doing the area under the curve from f of x. So if I break this into two parts, and instead I do, here's f of x. Well, maybe looks a little different, but same idea. F of x, right? And if you're finding the area under the curve from A to B, we're still going from A, and we're still going to the same B. We'll say that's B. Then I want to find all this area under the curve, right? And before, when we did integration, that is just the integration, oops, let me change the blue, the integration from A to B of f of x dx. And if we do the g of x, same idea. What if we have g of x over here, breaking it apart, and for our g of x, we're going to go from about here, we're going to go down, and then we're going to go up, and we're going to say that's B, and this is A, and now we're finding the area under that curve, which is all of this area. Right? Those are two different problems. This would be the integral from A to B of g of x dx. And how do we find the area between them? Well, we would subtract them. If we take this area right here that we had down here, hang on, let me do a little better than that. Let me exaggerate a little bit. If this is g of x, and we subtract all of this area off of the f area for f of x, will we get the region between the two curves? Exactly what we will do. So we will subtract these, and that means that the integral from A to B of f of x minus g of x dx is equal to the area between the curves. And what we did was we subtracted the upper curve. Well, actually, we subtracted the lower curve from the upper curve. So we did upper curve minus lower curve in order to get that area to be positive. And that's exactly how we're going to do it every time. But we can make our lives easier. Instead of having to do two problems, we can just approach it where up above where we found L here. We just found L here. This is L. Oh, I didn't want that color. Hang on. Oh, what did I get rid of? Oh. What I can do is, let's change this to purple. And this L right here, it's the shortcut. Because if you integrate that L, you're going to get the same thing. And it's what it is that length, that the length between the curves, that's the shortcut that gets you to just one problem instead of having to two problems and subtract. So the key here is that you want to find the area between the curves, right? By using the length, this is L right here, this is L, that length on the drawing, which is the length between the curves, and you want to keep it positive, so you want the upper minus the lower. Okay, so what does this look like in an example? Let's do an example. For example 1, we are going to find the area between f of x equals to x squared minus 4x plus 3 and g of x equals to negative x squared plus 2x plus 3. And the question comes down to, okay, so how do we do that? Because Mrs. White, you showed us a picture. Well, I guess we need to make a picture. But before we make a picture, they only gave us two curves. They didn't give us any limits of integration. So that means we have to go find the limits of integration. And the way we find the limits of integration is we find points of intersection. So the first thing we're going to have to do is we're going to have to find, so first thing we're going to have to do, step 1, find points of intersection. And I abbreviate in POI when you're doing work, but when I want you to do a fill in the blank, don't say POI. All right, so to find points of intersection, we set the two things equal to each other. And by the way, I can graph these really fast. You want a sketch of them. The easiest way to do this is just set them equally to each other. But I'm going to go ahead and tell you right now, I'm already suspicious because I'm looking at f of x. And it has a positive coefficient right here. This is positive. So that means it's got to be concave up, which means it's probably the lower. Doesn't have to be, though. And this negative tells me that's concave down, so that's probably the upper, but it doesn't have to be. We could do a saddle instead, and I'll show you an example of that later. But anyway, first I'm going to set those two equal to each other. So I'm going to say x squared minus 4x plus 3 is equal to negative x squared plus 2x plus 3. I'm going to move everything over to the right-hand side. So I end up with 2x squared. And then I'm going to end up with minus 6x. And then I'm going to equal to plus 6 equals 0. Sorry. And then, oh wait, I'm subtracting 3. That's 0. I knew something was wrong. So 3 minus 3 is 0, so it's just equal to 0. I factor out a 2 and an x. And that leaves me with x minus 3. And since that's equal to 0, that means that x equals 0 or x equals 3. So those are the x values for my points of intersection. I have to go find the points, but these are the x values. And you just need, for graphing purposes, you just need whole numbers. You don't need anything weird. So just make two tables real quick. Make an f of x table. So this is going to be f of x. This is the x squared minus 4x plus 3. And then I'm going to have g of x. G of x is equal to negative x squared. And it's plus 2x plus 3. And I'm going to make a little table. This is an x and a y table. And this is an x. Oops, got a blue. An x and a y table. And I know if I put in 0, I get 3 for both of them, which that makes sense because that's a point of intersection. Didn't switch colors. And then I'm going to go ahead and plug in nice numbers like 1 and 2 because it's not that hard. And I need to put in 3 because that's another point of intersection. I'm going to put in 3 into g of x, and that's going to give me negative 9 plus 6 plus 3. That means that's 0. Some tool keeps popping up on me. And then for the other one, I'm going to plug in 1, I'm going to plug in 2, and then I'm going to plug in 3, and I plug in 3 in here, and so it's 9 minus 12 plus 3. That's going to give me 0 also. So notice, our points of intersection match. And then, so that worked. And then now we can quickly plug these in and find what the curve looks like. You can figure out which one's upper and which is lower. You should sketch it anyway, but we're going to practice sketching for a reason. All right, so I plug in 1. So I have 1 minus 4 plus 3. I have 0 there. And then I plug in 2. And I've got 4 minus 8 plus 3 gives me a negative 1. For the other one, I plug in 1. I've got -1 plus 2 plus 3 means I've got 4. Then I plug in 2. That's -4 plus 4 plus 3. I need that's going to be a 3. And you'll notice that, hang on, let me change the green on this. You'll notice that g of x values are higher in between the points of intersection. This has got to be, looking at this, does this have to be the upper curve? And does this have to be the lower curve? Yep. And remember from my telling you about concavity that it was pretty clear what it was going to be? So this is lower curve. So it's going to have to be g of x minus f of x in this case. So finishing up this problem real quick, because it's not hard. If we were to sketch it, I will sketch it for you really fast, because it's really easy to sketch for this one, because there are my points right there. So I'm going to go 1, 2, 3, 1, 2, 3, and then I have to go down 1, and I have to go up 1 more. There we go. So I 0. So we start off, I'm going to graph this with purple. This will be purple. So I'm going to start off, oh actually no, let me graph in blue and green. So with for f of x, I start at 0, so it's 0, 3, and then, hang on, it's wigging out on me. 0, 1, 2, 3 for f of x, and then 1, 0, and then 2, -1, and then 3, 0. So that's f of x. And then there's g of x. For g of x, same starting point and stopping point, but I'm going to go, for 1, I'm going to go to 4. For 2, I'm going to go to 3. And then I come down to 0. So it goes like this. And the region between that we're looking for, the area of the region between, oops, hang on, something went wacko on me, went way too far. Uh-oh. Okay, I have to redraw that now. Notice the region between. So to find that, I'm going to say this is representative length. We're going to say that length is equal to the upper one, which is g of x. So that's -x squared plus 2x plus 3 minus the lower one. So this is upper, which is g of x. This is lower. So this is g of x. This is f of x. And f of x is x squared minus 4x, and then it's plus 3, so it equals to the -2x squared plus 6x. So I have to integrate that. So now I have my problem. My area is equal to the integral from 0 to 3, which are the x values. So this is a, and this is b. And then I want to integrate the -2x squared plus 6x dx, which that's easy. What's the antiderivative of -2x squared? It's equal to -2x cubed divided by 3. So it's -2x cubed divided by 3, and then the antiderivative of 6x is going to be 6x squared divided by 2, which just gives me 3x squared. And I am evaluating from 0 to 3. So remember, when we do our definite integrals, we always plug in the first one first, the upper one first. So that's going to be -2 times 9 over 3 plus 3 times 9, which is 27, minus 0, right? And when you simplify this, the 3's cancel out. That becomes -18 plus 27 equals 9. So it has an area of 9. And that's enough. We'll finish up the rest in class.